Hello and welcome to another episode of the pcalc series. So last time we found out that we actually need to do authentication with X11. We need to do MIT-MAGIC-COOKIE-1 or whatever it's called, authentication. So we're going to be starting on that today. The other thing I seem to remember in our error handling for platform common, when we abstracted the allocations, yeah, I was remembering right. So I remembered we casted these to size t, but that's supposed to be a signed comparison. So we probably want to cast that to signed size t. Assuming we have that defined. Yes, we do. So I think it was just those two. And we still need to fix up the error handling everywhere we use system calls, but we're going to do that later. So I'm going to switch over to platform X11. Now, let me see here. So there's X security manual page. I'm wondering if this is documented in the protocol documentation. It's interesting because you know, when we run this, we're getting 0 rather than 1. So it's not like if we try to connect to it without authentication, it doesn't tell us that we need to authenticate. It doesn't give us the authentication reply thing. Instead, it just gives us a failure saying no protocol specified. So let's search here. I want to see if MIT-MAGIC, looking like that's not getting picked up here. Maybe cookie, search cookie. Let's search authentication. So yeah, there's a separate authorization protocol. So we're gonna need to figure out where the MIT-MAGIC cookie authentication protocol is specified. And we can also read the XUB source code to see how it does it as well, which we'll most likely be doing. So yeah, I think all we're going to need to do is put the cookie in data, and the name is going to be set to MIT-MAGIC-COOKIE-1. I believe that's how that was done. So let's search MIT Magic Cookie 1 again. It seems like we just need to read the cookie from this x-authority file and send it in plain text to the server. But see, what I want to know is where's the protocol specified? There must be a protocol document for this. Here's some documentation from Oracle for Solaris. But it's looking like this is just a little paragraph detailing what we just saw. So when the server is started, the magic cookie gets created and it's put in that x-authority file for the user. And then whenever a client connects to the server, the client sends that magic cookie to the server as part of the connection packet, and as we saw, that's the data part of that struct we're sending. So then that cookie just gets compared with the server's cookie, and then the connection is allowed if it matches, and it's denied if they do not match. But this is not like a proper spec. I was expecting there to be some kind of official spec documentation of this stuff. But if there is, I'm not sure where you would find it. Okay, here is from x.org security documentation. So they've probably got a secondary document for this stuff. So yeah, this is saying that MIT Magic Cookie is the most popular scheme, and most desktop distributions make use of this method. But I don't know if they have like you know, I was just expecting them to like have a PDF that detailed the authentication protocols, but maybe I'm expecting a little bit much from these guys. I mean, it's pretty simple. The whole thing is described in a little paragraph, as we've seen. It's just you read a file and send the data. That's pretty straightforward. But, you know, I don't know, I just still imagine in my head that there would be more documentation, something that looks a little bit more official. Hmm. Looking like these are all extensions. I don't know if authentication would be considered an extension. There's MIT shared memory extension, but I don't believe that's what we're looking for. Closest thing I can think of is session management from the documents that I'm, skimming over here. Looking through the list, the closest thing I can think that it might be documented in is in session management, but it's probably not. There's probably not like a PDF detailing it. is my guess at this point. Let's just search MIT. So yeah, it's not in this. You know, I think at this point, the best thing we can do is assume that the documentation is only the web page we saw that had a few paragraphs about it from x.org. That's like the most official documentation of this stuff that we've seen. Yeah, we can maybe search on the website. See if it gives more hits. So there's a few hits. Wiki X11R4, X11R6. There's the security page that we already saw. There is the new X developers, or the X new developers guide. Communication between client and server. So this just rehashed the information we already knew. Again, it didn't tell us where this stuff is like documented. So let's take a look at the R6 one. We're on what, R7 or something? 7.7. But this is the one that had a hit on it, so we're gonna So it looks like the only hit for MIT-MAGIC-COOKIE-1 is this little bullet point. Requires MIT-MAGIC-COOKIE-1 authentication from clients. Talking about a simple session manager. So yeah, it looks like there's not a better better document. I mean, we got all the information we know, but I just think they should have put it in the protocol specification. You know, like either have it be part of the protocol spec or have a, you know, separate specs for the different authentication protocols. Rather than just having it, you know, as a little aside in random web pages. But anyway, we should jump into implementing this stuff. So first thing I want to do is I just want to print it out. It looks like it's empty though. Oh no, it's got bytes in it. So yeah, it's just got some garbage bytes in it. It's got the protocol name embedded in it. You see MIT-MAGIC-COOKIE-1 in there. So it sounds like all we need to do is read that file, put it in data, put MIT-MAGIC-COOKIE-1 in the name, and then send that in when we do our connection. That's my current understanding, but I want to take a look at the XCB source code. Okay, so we have this connect to display with auth info, which when you do XCB connect, it's really just doing connect to display with auth info. It parses the display. It does XCB open. Now I believe what happens here is we do if XCB get auth info. So it gets the auth info for the display. And then it does this XCB connect to file descriptor with the authorization stuff. Which is not defined in this file. And neither is XCB auth info type. So let's search. Okay. let's open up all the source files. Now line 216. Okay, so it's got a name length, the name string, and we see that's what's going to hold MIT-MAGIC-COOKIE-1. Data length, which I believe is 128 bytes for MIT-MAGIC-COOKIE-1. That's what those the documentation was saying. And then the data, which is what we read from the file. So that's how they're doing that. But I think when we actually send it, we send it in the structure we're already sending. The connection request structure. The stuff. Or I think these are supposed to be the length. This is the length of the protocol name. This is the length of the data. And then it's after the padding that the actual stuff is placed, if I remember correctly. So if we go back to this document, okay, that's not what I want. Go way down here. Okay, yeah, so here we see this is the padding. So above it, we have the length of the protocol name, length of the protocol data. And so I'm pretty sure we already know those. This is the length of MIT-MAGIC-COOKIE-1, and this is 128. And then this is going to be MAGIC-COOKIE-1. And this is going to be the data from the file. But we need padding between them, of course, and stuff. So we need to construct memory that looks like this, basically. And then we need to send all of this stuff to the server. But let's continue investigating how they did things. So yeah, they do this XCP connect to file descriptor after doing XCP get auth info. First thing I want to look at is the XCP connect file descriptor. So that's defined in XCP con.c. So they pass in their auth info structure and their file descriptor. Ooh, excuse me. So they do an allocation for the XCB connection type structure. They set the file descriptor to the one that was passed in. And then they're going through this stuff. Oh yeah, I remember seeing this stuff. So they do the set file descriptor flags, the pthread mutex in it. Then there was the XCB in it and the XCB out in it. And then they wrote the setup. And then they read the response. And then they do the extension in it and the XID in it. And so really the part we care about is where they do the actual write setup. Which is in this file. So this is taking the connection structure and the auth info. So here they set all this stuff up. And then we have auth info because we get it from the get auth info call. So we set out.authorization protocol name length equals auth info name length. And they're putting the actual name in the IOV base. Then the IOV length gets the padding for the name length as the protocol specifies. They set the pad into the IOV base. Then they do the data length, the data, they pad it. So yeah, I don't really understand the IOVec system that they're doing here, but I understand what we're doing. We're setting up the memory to look like this, right? So we've got like one of the parts is this, right? And then the next part is this, and then the next part is the padding because that needs to be dynamically calculated, and then the next part is this, and then the final part is the padding that again needs to be dynamically calculated. So that's what these parts are. And the length and the base for each IOV, whatever these things are that we're indexing into. So like the parts holds the different parts and there's a count. And so, you know, they write one, they, you know, go to the next, they write it, and, you know, and it goes down. So like here they're setting the length, right? So they don't increment the count. So when they do this one again, we're accessing the same member, right? But we're going to take the IOV base thing, and that's the actual payload. right? So each member of the parts has a length and a base. The length is the length of the thing, and then the base is the payload, right? So the first part, again, you see, oh, and they did break it up into the padding at the end of the setup request. I just have that baked into the structure, but they have it as a separate part, I guess. And pad is just defined as three characters, so 3 bytes. But yeah, so the way I'm understanding how this works is with the IOVEC structures. So you just have an array of the number of parts you need, and then each one of the IOVECs is a, holding the length of the part and the payload of the part. And then when you go to send, what it's going to do is write each part, and it writes the payload as many bytes as specified by the length. That's my understanding here, just from, reading the code. So I think IOVEC is like a Linux thing though, like part of whatever. I want to see if IOVEC is in my Linux book, so just give me a sec here. Yeah, so this is scatter gather IO. There's read-v and write-v. The read-v and write-v system calls perform scatter gather IO. Instead of accepting a single buffer of data to be read or written, these functions transfer multiple buffers of data in a single system call. Oh, that's convenient. We should do that then. So what it does is, these we can't just have a structure for what we're sending, because we need to dynamically pad. So like the number of bytes of padding depends on the things we're sending, right? So we can't hard code a number of bytes for these. So the problem is, like, we can't have a single structure that we're gonna send. You'd think you could just like allocate the memory that you need for the entire thing, figuring it out as you go, get it all allocated, and then set it up in a buffer in memory. So it would need to be dynamically allocated, but you could set up the memory and then send that. But I guess Linux has built into it something to help us out here, where instead of doing that, are just doing multiple writes back to back, we can do a scatter IO, or scatter gather IO operation, we can do a write-v call instead of a normal write call. And so then it can take all of our parts that we're building up and just send it all in a single system call. So we don't need to incur the penalty of multiple context switches as we, do multiple system calls. That seems like a cool thing that would be useful. So, I mean, it's not like the performance really matters for pcalc. It's not like we're writing a game or something. We're writing a little calculator. But I think I want to do the IOVEC stuff now that I'm seeing this. It sounds like it's pretty simple. The IOVEC structure is just a void pointer, IOV base, and then after that is size t IOV lang, IOV len, that is, for the length. So it's a very simple structure that we can define, and then we just need to define those system call wrappers, which, we've already seen how to do that kind of thing. And from there, I guess you just do a write-v, and you should get what you need. Write-v takes a file descriptor, a pointer to IOVEC structs, and an int specifying how many it's pointing to. The number of elements in IOV. There is a limit. susv3 allows an implementation to place a limit on the number of elements in IOV. An implementation can advertise its limit by defining IOV max in limits.h, or at runtime via the return from the call sysconf se IOV max. susv3 requires that this limit be at least 16. So we're not going over 16, so we don't care what it is. It says on Linux, IOV max is defined as 1024, which corresponds to the kernel's limit on the size of this vector, defined by the kernel constant uio max IOV. Awesome. It says the glibc wrapper functions for readv and writev silently do some extra work. If the system call fails because IOV count is too large, then the wrapper function temporarily allocates a single buffer large enough to hold all the items described by IOV and performs a read or write call. So yeah, that's what I was saying we could do instead of using the scatter gather IO. We could just allocate a buffer big enough to hold everything, write all the memory into it, and then do a single write call, a normal write call instead of a write-v call. And it says, see the discussion below of how write-v could be implemented in terms of write. So we could do it that way, but the way I see it is, why bother doing it that way if the kernel can do it for us? Like if the Linux kernel has a system call defined to do it for us, might as well use that. That's a cool feature of Linux, so let's use it. I just want to keep reading here because this is pretty interesting stuff. Figure 5.3 shows an example of the relationship between the IOV and IOV count arguments and the buffers to which they refer. I'm not going to draw out the stuff for you guys because this is more I know people enjoy watching this series, so it's kind of become like a proper series. Miblo hasn't done any annotations though, so he might not be planning on doing annotations for this stuff, and I'm not really I haven't been bothering numbering the episodes, and I don't save the recordings. And like I say, I'm not going to bother like writing out on Milton the diagrams in this book. And I'm treating this series less professionally than the main Risky Business stuff, because this is really just me doing work. This is just me programming, and it's not really meant to be like a proper series, but I do record them and put them up on YouTube now, and it's cool that some people enjoy that. So I know I enjoy that kind of content. Whenever I see Jonathan Blow watch his videos, I always get in the mood to do programming myself. So I imagine my videos might have a similar effect for some people. But so yeah, this is exactly like the diagram is showing us exactly what we were seeing in our code. There's a paragraph here about scatter input. The read-v system call performs scatter input. It reads a contiguous sequence of bytes from the file referred to by the file descriptor fd and places or scatters these bytes into the buffers specified by IOV. So that's kind of cool too. If we wanted to read something that has like variable length padding or whatever, we could scatter parts of what's being read into like what we want, I guess, through this or something. Each of the buffers, starting with the one defined by IOV 0, is completely filled before read-v proceeds to the next buffer. But I'm wondering if it can skip over padding, like if you can somehow tell it. I mean, I don't know how you would tell it to do that though, because I don't really understand the point of scattering. I guess it makes sense if you want to like scatter into like you're reading something that's returning what you want to treat in your code as multiple separate structures. I guess I could see why you might want to do a scatter read as opposed to a normal read, but the scatter read seems less useful to me than the scatter write, or the gather write, I guess you would call it. That seems way more useful to me. An important property of read-v is that it completes atomically. That is, from the point of view of the calling process, the kernel performs a single data transfer between the file referred to by fd and user memory. This means, for example, that when reading from a file, we can be sure that the range of bytes read is contiguous, and even if another process or thread sharing the same file offset attempts to manipulate the offset at the same time as the read-v call. So it does have useful properties if you're doing multi-threading, I guess. It might be more attractive in that environment. On successful completion, read-v returns the number of bytes read, or 0 if end of file was encountered. The caller must examine this count to verify whether all requested bytes were read. If insufficient data was available, then only some of the buffers may have been filled, and the last of these may be only partially filled. There's a listing that demonstrates the use. Using the prefix t followed by a function name as the name of an example program is our way of indicating that the program primarily demonstrates the use of a single system call or library function. Okay, so that was just a note on the structure of this book. Okay, gather inputs. So I want to read more about gather inputs. The write-v system call performs gather output. It's called output when you do a write-v. So the write-v system call performs gather output. It concatenates or gathers data from all the buffers specified by IOV and writes them as a sequence of contiguous bytes to the file referred to by the file descriptor fd. The buffers are gathered in array order, starting with the buffer defined by IOV 0. Like read-v, Write-v completes atomically, with all data being transferred in a single operation from user memory to the file referred to by FD. Thus, when writing to a regular file, we can be sure that all of the requested data is written contiguously to the file, rather than being interspersed with writes by other processes or threads. So again, this stuff is useful in a multi-threading context. As with write, a partial write is possible. Therefore, we must check the return value from write-v to see if all requested bytes were written. The primary advantages of read-v and write-v are convenience and speed. That's what I was thinking. I was like, you know, this sounds convenient and performant. So yeah, they're really primarily good for convenience and speed. For example, we could replace the call to write-v by either code that allocates a single large buffer, copies the data to be written from other locations to the process's address space into that buffer, and then calls write to output the buffer, or a series of write calls that output the buffers individually. So yeah, that's exactly what I was saying earlier, that those would be the two ways you could do it. And I was like, oh, so this IOVEX stuff is just a convenient way to do that, and it's more performant than doing the multiple write calls. So yeah. Yeah, I hit the nail on the head, I guess. Performing scatter-gather I/O at a specified offset. Linux 2.6.3 added two new system calls that combine scatter-gather I/O functionality with the ability to perform the I/O at a specified offset, preadv and pewritev. These system calls are non-standard but are also available on the modern BSDs. So I don't think we need that. I think we can use the normal read-v and write-v. We don't care about the offsets. Then this chapter goes into truncating a file, non-blocking I/O, I/O on large files. That's the kind of thing that would be useful for like you know, a project like 4Coder where you're, I know Alan Webster has 4Coder designed to be able to work well with very large files. So I imagine he knows this kind of information about I/O on large files. But we don't care about that for pcalc. The only file we care about right now is the one for the little cookie. The actual program won't be doing any file reading or writing. Just talking to a socket for X11. The file offset bits macro. The dev fd directory. Creating temporary files. Summary. Exercises. So yeah, I'm gonna say we've done our research, and we've decided we are going to implement write-v. I don't know if we're gonna need read-v. I feel like we're not gonna need read-v. But maybe we'll change our mind about that. Now that I know how the IOVEX stuff works, it's actually really simple. It's just like two syscalls in a really simple structure. And it's really actually pretty cool. So yeah, we're going to be using that stuff. Let's head over to Linux, the Linux stuff. And we're probably, I'm running out of time, so probably not going to be able to get this implemented today, but we're going to start on it. Okay, so let's decide where we're going to put it. We have sockadder, sockadder yun. I don't know if we need the original sockadder anymore. I think we maybe stopped using that. Or no, we do use it for connect. So never mind. We'll keep it around. So I guess if we're going in alphabetical order, let's take this comment and put it on its own line. Because if we're going to be adding more structs to this platform, we don't want to have to move that all the time. So what was this struct called? IOVAC? Yeah, it's just called IOVAC. And we have a void pointer to IOV base, and I think it was a size t IOV lang. I'll double check that. Yeah, that's correct. So that's all IOVAC is, and then we just need 2 syscalls. So that should be pretty simple. Let's see here. So where did we put write and read? So they even take like the same number of arguments. It just, instead of being a file descriptor, a buffer, and a count, it's a file descriptor, a pointer to IOVAC, you know, an array of IOVAC, and then the count. So this becomes write-v. And again, we're going to assume that the syscall returns error no values, like the raw syscall returns error no values on error, and on success, it should return the number of bytes. So we have intfd const, and this isn't a void pointer anymore. This is an IOVAC pointer. And we just call it IOV. And this is only an int because of that, you know, limitation we saw and how many you can actually pass to it. I think it was called CNT, IOV CNT, something like that. Yeah, that's what they called it. Not that the names matter. You know, the names don't really matter, but I try to keep to the convention, like the normal convention. The only major thing I've changed is like I type def my structs. But that's the nice thing about implementing from scratch. You can have whatever conventions you want. You can go crazy if you really want to. So yeah, I'm gonna put my Linux book away now. And next time, we're going to finish up this implementation. And then we'll continue implementing authentication. So, thank you guys for watching, and I'll see you in the next episode. Stay risky, everybody.